Lesson 2.3 is talking about polynomial functions. You'll find this on page 185. We've already talked about polynomial functions in the past in Algebra 1, in Algebra 2. In this lesson we're going to go a little more in depth with polynomial functions and more specifically with their graphs. So to start off, let's look at a few examples of polynomial functions. First we have f of x equals 4, which we can think of the same as 4 times x to the 0 power, because we know that anything raised to the 0 power is 1, so x to the 0 power is 1, 1 times 4 is 4. G of x is equal to radical 3 times x to the first. We don't need to have that 1 written in there. If it's not written in there, it's understood to be a 1. Okay. H of x is equal to negative 2 times x squared plus 13x minus 400. And the last one, j of x is equal to radical 15 times x to the 10th minus 13x squared plus pi times x. So if we try to think about what do all of these functions have in common, and what do they have in common that makes them polynomial functions? Well, first thing we need to look at are the coefficients. All of these coefficients are real numbers. If we look at h of x, negative 2 and 13, we know those are real numbers. If we look at g of x, radical 3. Radical 3 is an irrational number, but it is still real. Even if we look at the last function, j of x, it has pi times x. Pi is an irrational number, but it is still a real number. So the first thing to be concerned with polynomial functions, they need to have real number coefficients. The second part of polynomials are the exponents. The exponents have to be non-negative integers, meaning 0, 1, 2, 3, 4, 5, and so on. If you look at all the exponents, in f of x the exponent is 0, g of x it's 1, h of x we have multiple exponents, 2 and 1, and same thing with j of x. But what they all have in common is that they are non-negative integers. So let's take a look at some non-examples. We have three different functions, k of x, p of x, and q of x. If we look at k of x, that has a coefficient of 3i in front of x squared. Remember from Algebra 2, I stands for an imaginary number. If you look off to the right, I equals the square root of negative 1. The square root of negatives, you know by now that you can't take the square root of a negative number, so that is what is wrong with k of x. That is not a polynomial because it has a coefficient that is not a real number. If we look at p of x, that has a coefficient of 1, which is why it's not written in there. It's understood to be there. So the problem with this is the exponent. It has a negative 3. You cannot have negative exponents in polynomials. Last function, q of x, we have exponents of 1/2 and 5/3. Those exponents are positive, but they are fractions. The exponents have to be non-negative integers. We cannot have any fractions. So coefficients and exponents are the keys to what we're looking at when trying to determine if a function is a polynomial. Next thing we're going to look at with polynomials is standard form. Standard form is basically taking the function and writing it from highest degree to lowest degree in descending order. Degree is referring to our exponents. So if we start with f of x equals negative 2x plus x cubed minus 7 plus 5x squared, if we rearrange those terms from highest degree to lowest degree, the function would be f of x equals x cubed plus 5x squared minus 2x minus 7. So we're looking at the exponents. We have a 3 in our first term, then a 2, then 1, then 0. So we're going in descending order. That is standard form. We do not have to worry about what the coefficients are. We are only focused with the exponents. So next we're going to look at why writing it in standard form is beneficial. two main things we're going to be looking at when we write a polynomial in standard form. First thing is the leading coefficient, and the other is the degree. So suppose we have the function g of x equals 3x to the 5th minus 4x plus 1. This is already in standard form because if we look at our exponents, we have an exponent of 5, 1, and 0. So it's going in descending order starting with the largest exponent. So now we just have to look at our first term, 3x to the 5th. The leading coefficient is the number being multiplied in front of that variable term, so our leading coefficient is 3. The degree of the polynomial is the degree of the first term. So if we look at the exponent, it's an exponent of 5, so the degree of this polynomial would be 5. The next part of polynomial functions we're going to look at are the graphs of polynomials. So if we have the function f of x equals x cubed minus x, there's two main things we're going to emphasize right now. We're going to look at the extrema of the graphs and the zeros. We've talked about both of these in the past. The extrema are referring to any local min or local max values. The zeros are the x-intercepts of the graph. Where is the graph crossing the x-axis? So we get our graphing calculators out, and we want to graph the function x cubed minus x. I'm going to change my window from -3 to 3 and from -3 to 3. So if I graph this function, this is x cubed minus x. This looks basically like our cubing function we talked about at the beginning of the year. What we want to do is, are there any local mins or local max values? Looking at this function, looking at the graph, you should be able to see that we have both of those. If we go to second calculate, we can determine what that local minimum value is. So it asks us for our left bound. So our local min appears to be somewhere in this region, so I'm going to go to the left of that value, push enter, then I need to find my right bound, so I go to the right of that minimum value, push enter again, and I have my local min at approximately 0.58 for my x value and a y value of -0.38. Next, if I go second calculate and push number 4, I can find that local maximum value. So if I arrow over to the left to determine my left bound, clicked it too many times, push enter. Now if I go find my right bound to the right of that maximum value, enter, push enter one more time to get my guess, and I get an approximation of -0.58 and a y value of 0.38. So that's how we can find our local min and local max values, also referred to as the extrema of the graph. The other thing we wanted to determine were the zeros of the graph, which are the x-intercepts. So if we go to second calculate, there's also a button for us to find the zeros of the graph. When I click to find the zero, I'm looking for where it crosses the x-axis. First thing it asks me to find is the left bound. So I need to look at my graph. Going from left to right, my graph is increasing. So the left bound, in that case, is going to be below the x-axis. I'll push enter. My right bound on this first x-intercept, this first zero, is going to be above the x-axis. So if I push enter again, my first zero of this graph where it crosses the x-axis is an x value of -1. If I go through that same process, number 2 to 0, now I want to find this 1 where it crosses, appears to be at the origin. Now, this portion of the graph is decreasing. When I'm moving from left to right, my graph, my y values are decreasing. So my left bound is going to be above the x-axis. If I push enter, now I find my right bound, which will be below the x-axis. Push enter. Take my guess. I get an x value of 0, which is what we predicted. Now I can find the last one. Again, my graph is increasing, going from left to right. My y values are going up, so it's an increasing graph. So my left bound is 0, push enter. Then I find my right bound, push enter, and take my guess, and I get an x value of 1. So my 3 zeros of this cubic function, x cubed minus x, are -1, 0, and 1. We could have also found the zeros of this function algebraically. If we look at x cubed minus x, if we look at both those terms, we should see what they have in common. They have a factor of x in common. So if I take that factor of x out, I'm left with x squared minus 1. X squared minus 1 should look familiar from Algebra 2. That is a special factoring pattern. It's a difference of 2 squares. So this factors into x times difference of 2 squares, x plus 1 times x minus 1. So now I have my 3 factors. If we're trying to find the zeros of these factors, it simply means we're going to set each of those factors equal to 0. So we get x equals 0, x plus 1 equals 0, and x minus 1 equals 0. We solve these. X equals 0, x equals -1, and x equals 1. So 2 different ways we can find the zeros. First way, we found it graphically. Now we found it algebraically. Next thing we're going to talk about in this lesson is the end behavior of the graphs. Okay, what's happening as we go to the left? What's happening as we go to the right? As we go to the left, our x values are approaching -infinity. As we go to the right, our x values are approaching infinity. 2 different types of end behaviors. We have odd degree, which is referring to our highest exponent. Odd meaning numbers like 1, 3, 5, 7, 9. There's an odd degree for our polynomial function. If there's an odd degree, there's 2 different cases that we can have. Our leading coefficient could be positive, or the leading coefficient could be negative. So if you take a look at those 2 graphs, if it's an odd degree and the leading coefficient is positive, as our x values approach -infinity, our y values approach -infinity. That is what the limit is saying. The limit as our x values are approaching -infinity of our function f of x equals -infinity. As we approach x values to the right of our graph, approaching positive infinity, our y values are also approaching positive infinity. Okay? That is the case if the leading coefficient, the number in front of our highest degree term, is positive. Now, if the leading coefficient is negative, we can see our graph is slightly different. As our x values approach -infinity, as our graph is going to the left, our y values are approaching positive infinity. The y values are increasing. As our x values approach infinity, as they go to the right, we can see our y values approach -infinity. So these are going to be the end behavior, what's happening to the graph as it approaches the left, what's happening as we approach the right. This will always be true for polynomials that have an odd degree with these 2 different circumstances. The leading coefficient is positive on the left, the leading coefficient is negative on the right. Similar idea when we're talking about functions that have an even degree. Okay, even degree. That means our degree is going to be 2, 4, 6, 8, and so on. Again, we have 2 different situations. Our leading coefficient can be positive, or the leading coefficient could be a negative value. If our leading coefficient is positive, as we approach x from the left, as we're getting more negative with our x values, our y values are increasing. They're approaching positive infinity. Same thing is true as we're approaching right for our graph. Our x values are increasing, so our y values are both increasing. if it's an even degree polynomial. Both of our limits, whether we're approaching x from the left, negative infinity, or we're approaching x from the right, positive infinity, our y values are going to be approaching infinity. They're going to be increasing. Now, if we look at the right graph, our leading coefficient in this case would be negative. An example of this could be y equals negative x squared plus 2. Okay, that's in standard form. Our degree is 2. It's even. Our leading coefficient would be negative 1, so that's a negative value. Our limits in this case, as our x values approach negative infinity, our y values are approaching negative infinity. As our x values decrease, we're going to the left. Our y values are decreasing as well. As our x values increase, as we approach that graph as we're going to the right, our y values are also decreasing. So you can see by an even degree polynomial, whether we're going to the left or to the right, our values are either both increasing or they're both decreasing. So let's go through an example of how to determine the end behavior of a polynomial function. In this example, we have f of x equals 2x to the fourth minus x cubed. The degree of this polynomial would be 4, which is even. And the leading coefficient is 2, which is positive. Okay, so now we're going to look at what we just talked about on the last few slides. It's an even degree, and the leading coefficient is positive. So our limit as x approaches negative infinity of this graph will be positive infinity. As our x values are going to the left, they're decreasing. Our y values are increasing. The limit as x approaches infinity, as our x values are increasing, as our x values are going to the right, our y values, the values of our function, are increasing. They're approaching infinity. If it's an even degree polynomial, these two values have to be the same. We're going to go through another example similar to one we've talked about already in this lesson, finding the zeros of a polynomial. So we have g of x equals x cubed minus x squared minus 6x. We could graph this and find the zeros that way, but you can do that if you choose on your own. But I'm going to go through how we can find this algebraically by means of factoring. First thing we should always do if we're trying to factor is see if all of the terms have something in common. So we have g of x equals x cubed minus x squared minus 6x. If you look at those terms, we should see that they all have a factor of x in common. So if I take an x out of all those, I'm left with x squared minus x minus 6. X squared minus x minus 6. We're looking for factors of negative 6. Negative 6 and 1. 6 and negative 1. 2, negative 3. Negative 2 and 3. We're looking for the combination that when we add together give us a middle term, a b value of negative 1. If I take 2 plus negative 3, I get a value of negative 1, which means this factors into x times x plus 2 times x minus 3. So, similar to what we had earlier in an example, we take these three factors, set them equal to 0. X equals 0, x plus 2 equals 0, so if we solve that, x equals negative 2, x minus 3 equals 0, so x equals 3. Here are the three zeros of that polynomial function. A theorem in your book on page 187, okay, talking about the local extrema and zeros of a polynomial function. It says a polynomial of degree n has, first condition, n minus 1 local extrema. When we talked about this last year in Algebra 2, we refer to the turning points of the graph. If we have a turning point in our graph, meaning it's changing from increasing to decreasing or from decreasing to increasing, that indicates we have a local extrema. It's either a local minimum or a local maximum. Second condition is it has at most n zeros. So what that's saying is if we have f of x equals 2x to the fourth, just a basic polynomial. Our n, our exponent, the degree would be 4. So if we graph this function, we would have at most n zeros, which is at most 4 zeros, and there would be at most 3 turning points. Now, there doesn't necessarily have to be 3 turning points. There doesn't have to be 4 zeros. This just tells us how many at most we would have. When we're talking about the zeros of the function, we can also talk about the multiplicity, which is basically saying how many times a zero occurs. Okay, the definition of this is on page 189 at the bottom of the page. 2 different conditions we can have for multiplicity. We can have even multiplicity, so that zero is occurring 2 times, 4 times, 6 times. Or we can have an odd multiplicity, and we'll get to that in a little bit. Even multiplicity, if that zero occurs 2 times, 4 times, 6 times, so on, the graph touches the x-axis and turns around. So if we look at the graph on the right, this would have even multiplicity for our 0, x equals -1. We can see it's touching the graph at that spot. Approaching from the left, it's decreasing, it touches the graph at that point, and then turns around and goes the other way. Okay, that indicates even multiplicity. We don't necessarily know if that 0 is occurring twice or 4 times, but we know it must be even. If we're talking about odd multiplicity, the graph crosses the x-axis at that point. So if we're looking at this, this is a basic cubic function. You can see we're crossing the x-axis, so that means that 0 is going to occur either 1 time, 3 times, 5 times, some odd multiplicity, because it crosses the graph at that point. I think this will make more sense if we look at a specific example. So we have f of x equals x cubed. That is basically saying that we're taking x times x times x. Well, if we're trying to find the zeros of this graph, we have 3 factors. We're setting all of those equal to 0. X equals 0, x equals 0, x equals 0. Okay, pretty straightforward. This is occurring 3 times. So x equals 0 has a multiplicity of 3. 3 is an odd number, so by using our definition of multiplicity, at that 0, the graph should cross the x-axis. So if we look at our basic function, x cubed, and graph it, zoom 6, we can see at x equals 0, it crosses the graph. Odd multiplicity. Now we're going to look at an example that has potentially even multiplicity. If we look at g of x equals x squared plus 4x plus 4, and we want to find the zeros of this graph. We could graph it out graphically using our graphing calculator, or we could solve this algebraically. X squared plus 4x plus 4 conveniently factors into x plus 2 times x plus 2. We have 2 factors, set each of those equal to 0. X equals -2. X equals -2. So our 0 of x equals -2 has a multiplicity of 2. It occurs twice. So by our definition, if it has a multiplicity of 2, it should touch the graph at that 0 and turn back around. So if we go and graph this function, x squared plus 4x plus 4. Zoom 6, our standard viewing window, we can see at our 0 of -2. It's decreasing, it touches the graph at that point, and turns back around. It does not cross the x-axis, it touches the x-axis and turns around. That is indicating even degree. Last thing we're going to briefly talk about in lesson 2.3 is IVT. That stands for the intermediate value theorem. Alright, this is on page 190. It has a long definition for this theorem that you can take a look at. We'll talk about this more in class together and the basic ideas behind it. We're not going to go too in-depth with this theorem. It's needed more for calculus. So those of you that take calculus next year, we'll talk about the intermediate value theorem more then. What you need to do now is, on page 191, look at example 9. It is modeling how to design a box. We're starting with a piece of cardboard. We have a certain volume we want to have. So similar to what we did in lesson 1.7, designing a box that has a given volume. Take a look at that, and then you can start on the homework.